Hello viewers, good afternoon. Professor T. N. Oza here. Today I am going to present before you yet another new video based on photoelectric effect. You must be familiar with this name because it is taught in schools also. It is a very important concept and one of the pillars of quantum mechanics. In this video we will discuss the concept, the applications and other related aspects of photoelectric effect. The following points will be covered in detail: introduction, light waves, theory of photoelectric effect, why wave theory of light cannot explain it, work function of some metals, graphical display of photoelectric effect, numerical problems, applications of photoelectricity, and finally, a few practice questions. These points will be discussed one by one. Introduction. When light of certain minimum frequency is made incident on a metal of low ionization potential, ionization of the surface atoms may occur, resulting in the emission of electrons, the so-called photoelectrons. These electrons can complete an otherwise incomplete electric circuit and therefore cause conduction of current, as may be indicated by the lighting of an electric bulb provided in the circuit or by using other current measuring devices. The generation of electricity in this way is called photoelectricity. These days, this phenomenon of photoelectricity is being exploited in the solar cells on quite a large scale for getting clean electric power generation. Sir J. J. Thomson is credited with the first record of this kind of phenomenon, although it was named so later. Einstein in 1905 gave adequate mathematical explanation for this phenomenon using the quantum theory of radiation earlier propagated by Max Planck. Here is the photograph of the Professor Einstein, a celebrated scientist and a very good human being. Light waves. In our discussion of the topic of photoelectric effect, we need to clearly understand the nature of electromagnetic radiation. The electromagnetic radiation travels as waves or as corpuscles called photons, the so-called dual nature of light. Photons of a specific frequency of unit per second or hertz or cycles per second, abbreviated as CPS. The theory of photoelectric effect is understood in terms of photon concept, that is the corpuscular theory of propagation of light. But the wave nature is more explicit in understanding several other characteristics of light. Suppose that a light wave is traveling along the x direction, then its speed c in meter per second is given by a product of its frequency f per second and wavelength l meter. That is to say, wave is the value of its frequency f per second and wavelength l in meter are related by the following equation: c equal to f times l, f equal to c over l, wave number f prime equal to 1 over l, energy E equal to hf equal to hc f prime. Here we have shown the nature of wave and some parameters. A wave is propagating along x direction. Then perpendicular to x direction, there is electric vector, and perpendicular to both x and y axis, that is along z axis, there is a magnetic vector. Electromagnetic waves are inherently associated with these two vectors. A parameter often used very often, wavelength, can be defined as two nearest points on the propagation axis whose x, y, z coordinates are exactly equal in magnitude and sign. That distance is called wavelength. Theory of photoelectric effect. The following points will clarify it. According to Planck's theory, Physics Nobel laureate 1918, light consists of photons of specific energy E, that is E proportional to frequency f, or E equal to h time f, where E is energy in joule, f is frequency in per second, h is Planck constant having numerical value of 6.625 into 10 to the power minus 34 joule second. Second point is each metal has certain characteristic value of ionization energy, minimum being 2.1 electron volt for cesium, lowest value. Third point is if the incident photon energy HF0 is exactly equal to the ionization energy of that particular metal, ionization may take place and an electron is ejected. This value of energy is often termed threshold energy or work function in terms of frequency, threshold frequency, in terms of wavelength, threshold wavelength. In thermodynamic terms, work function of a metal is defined as the thermodynamic work needed to remove an electron from the surface atom of the metal in a point in vacuum. Emission of electron does not take place if the incident photon frequency is lower than the threshold frequency for that very metal. No matter how long duration the light is made to fall on the metal or how much is the intensity. If threshold condition is not fulfilled, ejection of electron won't take place. This is a very important point to note. If the incident photon energy HF is greater than the work function W or phi, the ejected electron will flee away with a velocity u and kinetic energy equal to the difference of energy, that is HF minus HF0. Thus, HF equal to HF0 or phi, that is work function, plus kinetic energy of electron, half MEU square. The kinetic energy of the flying electron is given by equation 3, Einstein photoelectric equation, Physics Nobel laureate 1921. Half mu square equal to HF minus HF0. Thus we can calculate velocity of the flying electron. The intensity of the photoelectric current thus generated is directly proportional to the intensity of the incident radiation, provided that it meets the threshold condition. If threshold condition is not met, that is incident frequency is lower than work function frequency, then rejection of electron won't take place. Why wave theory of light cannot explain photoelectric effect? The wave theory of light says that the energy of radiation is directly proportional to its intensity. If the wave theory of radiation was to be accepted as such, increasing the intensity of the beam without increasing the frequency should have caused photoelectric effect. But when light of frequency lower than the threshold frequency for that metal is made to strike the metal surface, no electron is ejected, no matter how much intense the beam is. This observation shows The inadequacy of the wave theory of light in explaining the photoelectric effect. On the other hand, the quantum theory of radiation satisfactorily explains the phenomenon. Radiation consists of bundles of energy packets called photons, HF. The energy of each photon is given by h times f, h Planck constant, f frequency. Energy is required to dislodge an electron from the outermost electron cell of an atom on metal surface must be exactly equal to an integral multiple of HF, photon integral multiple of photon. Ref refers to a specific frequency. Essentially speaking, the photoelectric effect is well understood by accepting that the light wave behaves as a stream of teeny particles or corpuscles called photons, which fall on metal surface, and a collision with electron causes ejection. Work function for some metals is given here in electron volt units. Lowest value is for cesium, next lower is for potassium and sodium, nearly equal. Calcium is also not very high, 2.9 electron volt. For other metals, it is quite high. Here I have shown two graphs. In one graph, kinetic energy of photoelectron shown along y-axis increases proportionately with the intensity of radiation provided the frequency is higher than threshold frequency. In the second graph, kinetic energy of photoelectron is plotted against frequency. Zero refers to threshold frequency. And you see W here is negativity work function. Frequency is shown along x-axis. Before attempting numerical questions, we must understand various interconversions. Energy is given by H cross F equal to H cross F over L. Here F is frequency, C is speed of light, L is wavelength. Some other interconversions are given here. An example, suppose we consider light of 3000 angstrom wavelength. Then we can calculate a number of parameters from this. Energy can be calculated using H C over L. H Planck constant, C speed of light, L is wavelength. One precaution is must. If wavelength is given in units other than meter, it has to be converted into meter. And we get the energy value as 4.136 electron volt. Now we consider kinetic energy half mu square. This is equal to incident energy minus work function 4.136 electron volt minus 3.1 electron volt. So kinetic energy becomes equal to 1.036 electron volt. From this data, we can calculate velocity of electron because m is constant. So velocity of photoelectron u can be calculated using the formula shown here, and we get the result 6.04 into 10 to the power 5 meter per second. In summary, we can solve different numerical problems using similar manipulative scale. Applications of photoelectricity. The sun is source of inexhaustible clean energy. With the fast depletion of fossil fuel, increasingly more and more attention is being paid to the harnessing of solar energy for electricity generation. Some common examples are magic eye or electric eye in the doors, which can open doors from a remote place, light meters used in photography, solar panels, photostatic copying, etc. Cesium, a group 1 alkali metal having atomic number 55, is the most preferred metal used in photoelectric cells because its ionization requires less energy than any other metal. Some precautions need to be exercised. For example, applying a voltage in excess of the operating voltage range or applying AC power 100 volt AC or greater to a DC sensor may cause explosion or burning. So precautions are must. Practice questions. One question is, given that frequency is incident radiation, F W is the work function HF0 of the metal, and K is the kinetic energy of the ejected electron. Draw a hypothetical graph and determine the slope. Hint is given here. The straight line equation says y equal to mx plus c. See, in this equation, x is an independent variable shown along x-axis. Y is a variable which is dependent on x shown along y-axis. C is an intercept. Its value may be 0, may be positive, may be negative depending upon the situation. And its slope. So if you plot y versus x, the slope of the line will give you f value. And if the line passes through 0, then c will be 0. But if the line cuts the y-axis on in negative side, the intercept will be negative. If it cuts the y-axis on positive side, the intercept will be positive. So in this manner, you can show graph, you can calculate slope, you can calculate intercept, and graphs are self-explanatory in many cases. Another practice question is given here. Some more questions are asked. One question is why red light fails to cause emission of photoelectron. Hint is given because it has low energy. What causes emission of photoelectron? Collision between photon of energy greater than work function W with the surface electron of the metal. And the question says, draw a circuit diagram to demonstrate the photoelectric effect. It is available in most of the elementary books. You can even design it. Question 6 is convert frequency of 4000 decimal per centimeter into frequency per second into wavelength. Various conversion on one of the slides I have given how to convert them. Here also hint is provided. So with this discussion, if you practice this video 2-3 times and consult a book, you can thoroughly understand it. You must remember in mind, this is one of the basic pillars of quantum mechanics. So thank you very much. Thank you.